In this episode, we are going to review cgroups, commonly referred to as control groups. These provide a mechanism for easily managing and monitoring system resources by partitioning things like CPU time, system memory, disk and network bandwidth into groups, and then assigning tasks to those groups. Let me try and explain what control groups are and what they allow you to do. Let's say, for example, that you have a resource-intensive application on your server. Linux is great at sharing resources between all the processes on a system, but in some cases you want to allocate or guarantee a greater amount to a specific application or a set of applications. This is where control groups are really handy. For example, let's say that you wanted to assign or isolate an application's resources. Let's create two groups. Group number 1 will be used for our operating system, and group number 2 will be used for our application. Then we can assign resource profiles to each group. Let's focus on group number 2 for a moment. Typically, when you create a group, you already have a problem in mind. So for the sake of this example, let's say that we wanted to manage CPU, memory, disk and network bandwidth for our application. So I would create a group and assign resource limits to this group, something like this. Keep in mind, the application knows nothing about these limits. This is happening outside of our application. So any application that is assigned to this group cannot use more than 80% of the CPU, 10 gigabytes of memory, 80% of disk reads and writes, and finally 80% of our network bandwidth. Once the group is created, we simply need to add our application's process IDs or PIDs into a file, and your application is automatically throttled. This can happen on the fly, without system reboots, and you can adjust these limits on the fly too. I just wanted to mention that our application will be allowed to spike outside these percentage limits, but if there is any resource contention, our application will be throttled back to 80%. Monitoring is also baked in from the start, so we can monitor resource consumption for any application that is assigned to this group. Things like CPU cycles used, the memory profile, IOPS, and bytes written and bytes read from the disk, along with any network bandwidth used. Let's jump back to the previous illustration and use a different example. Let's say that we have an environment where we are hosting virtual machines. Instead of just having two groups, one for our operating system and one for our application, we can have many groups, one assigned to each virtual machine. For example, let's say that we're worried about a virtual machine saturating the network link or disk IOPS. We can limit the impact by using control groups, which can be really handy. There's plenty of documentation out there. The Wikipedia pages give a pretty good overview. If you're interested in a little bit of history, work was started on control groups by two engineers at Google in 2006 under the name process containers. But in 2007, it was merged into the Linux kernel and renamed control groups, or cgroups. The kernel docs are amazing and should be considered the definitive source. I will reference them in the upcoming examples. Red Hat also has a great chapter in their manual about control groups. I have linked to all these sites in the episode notes below. Alright, let's move on to the examples. Let's go ahead and install libcgroup on a CentOS 6.4 machine by running yum install libcgroup. I always like to see what files we just installed. This helps me know where to look for scripts and configuration files. Let's run rpm query list libcgroup, and then pipe the output to less, which will give us a listing of all the files and their locations for the libcgroup package we just installed. So libcgroup places a bunch of utilities in /bin, creates a /cgroup directory where we can mount the various control group subsystems. Then there are several configuration files and init scripts in /etc, followed by a couple more utilities in /bin, and then it looks like the rest is just documentation and man pages. Okay, so we noticed that a new /cgroup directory was created. This is where the cgroup virtual file system will be mounted. There is nothing in there now, but before we populate it, let's review the /etc/cgconfig file to see what mounts we can expect. You'll notice in here that it says by default mount all cgroup controllers to /cgroup, followed by the controller name. Then down here you can see all the cgroup subsystems are defined. Okay, now that we know what to expect, let's go ahead and mount the control groups. We do this by running service cgconfig start, then let's ls/cgroup again, and you will notice that there are several directories in here now. Each one of these directories can be used to manage a control group subsystem. For example, the block IO directory can be used to manage block devices, or these CPU directories can be used to manage CPU resources. Let's go ahead and list the directory contents of the block IO directory, where we can review what the directory structure looks like and talk about some common files that you're likely to interact with. First, you will notice that most of these files are prefixed with the controller name, in this instance block IO. This is useful because when you combine multiple control groups, let's say for example the block IO and the memory controllers, there will be no name conflicts, and it's clear what system you're interacting with. Each control group will always have these 5 files. First, we have the tasks file. This file contains a list of the process IDs, or PIDs, attached to this control group. So if you wanted to assign a process on a system to this control group, all you need to do is echo its process ID or PID into this tasks file. It's as simple as that. Next, there is the cgroup.procs file. This is similar to the tasks file, but this one contains the thread group IDs, which can be useful if you have a multi-threaded application. Next, there is the cgroup.eventControl file. This can be used to hook in a notification API of some type. Say, for example, that you want it to be notified when a process hits an out-of-memory condition or something similar. These next two, Notify on Release and Release Agent, work hand in hand. These can be useful for taking action when all the processes in a control group terminate. This works by setting Notify on Release to either true or false. True being that you want to take action, and false that it does nothing. The default value is false. So you would point the release agent at a script of your choosing, and then when the last process terminates in this control group, if notify on release is set to true, it will execute that script. This can be really useful for logging or getting notifications when all the processes in this control group terminate. Now that we know a little bit about the control group structure, let's create a new child group within the block IO control group. So we are in the /cgroup/block IO directory, and we want to create a new child group called test1 within the block IO control group. We just create a directory called test1. You can also use the cgcreate command, but just creating a new directory is pretty self-explanatory. Let's list the directory contents again. As you can see, our new directory is here. Let's change to this test1 directory and list the contents. So you can see that this directory gets automatically populated, and then it looks exactly like the parent directory with the exception of the release agent file. The release agent is only present at the topmost root level object. Just to show you the hierarchy again, we have the /cgroup directory, then the block IO subsystem, and then as a child of the block IO, we have a group we just created called test1. You can also use the ls/cgroup utility to display control groups. So you can see we have the block IO group, and then we also have a block IO test1 group. We will be using this notation in several upcoming examples. I think this plays well into our first example. Let's assume that we wanted to throttle reads or writes of a particular process or group of processes. Let's configure our newly created block IO test1 group to do just that. Before we begin, let me explain how we are going to run this demo. In the topmost window here, I'm going to run IOTop. This will give us a status of anything reading or writing to our disks, along with the rate. Then in the bottom window, I'm going to create a couple 3 GB files. We're going to compare the disk read rates for processes that are part of the control group to ones that are outside of the control group. I'm going to run dd. We're going to use /dev0 as the input file, and then the output file will be file-abc. Byte count is 1 MB, and we're going to do this 3,000 times, giving us a 3 GB file of zeros. You can see up in the top window here, IOTop is reporting that we are writing at around 500 megs a second. Then down here, dd has finished writing the file. I'm just going to create a second file called file-xyz so that we can compare files in a control group to ones outside it. I'm just going to list the files so that we can verify their sizes and know what we're working with. Before we go any further, let's just make sure that we flush any file system buffers to disk by running sync. Then let's run the free-m command to show our memory usage. Notice the memory used and the cached columns. Let's dump the caches since this likely contains bits of our files, which might skew any performance measurements we take. Let's drop the cache by running echo 3/proc/sys/vm drop caches. Then let's run the free-m command again, Notice how the memory used and cache columns both went down. Okay, now that we've flushed the file system buffers to disk and dropped any system caches, let's take a quick peek at the block.io controller documentation so that I can explain what we're about to do. Under the throttling section, there are a couple files that can be used to throttle read and write rates for block devices, along with their expected syntax. By the way, you can find this documentation, along with all the cgroup documentation, at the kernel.org site. I have provided links in the episode notes below. Let's focus on throttling the read rate. So we echo the device major and minor values, which we want to rate limit, or throttle, along with the rate in bytes per second to this file. So we still have IOTop running in the topmost window here. Then down here, let's list the control groups again by running ls cgroup. So we have the block.io controller and then the block.io test1 group under that. Let's go ahead and change into the test1 directory. We need to echo the device major and minor numbers along with the rate in bytes per second into this block.io.throttle.bytes per second file. But where do we get these major and minor numbers from? This is actually pretty easy. The machine I'm working on only has one disk, and that is /dev SDA. Let's just list all the /dev SDA entries. So you can see in the output here that we have these numbers. For /dev SDA, they are 8 and 0. These are the major and minor numbers we're looking for. So since the files I want to rate limit are stored on /dev SDA, we'll use 8 and 0. Alright, let's type our command using the syntax we learned from the documentation. Echo 8:0 5242880, and then pipe the output to block.io.throttle.read bytes per second. So we said echo device 8:0, that is /dev SDA, 5 megabytes in bytes per second, and pipe the output to the block.io.throttle.read BPS device. Let's just cat this file to verify our values were actually set. Before we test this rate limit, let's get a baseline for what performance is like without it. Let's use the dd command to read file-abc from disk and write it to /dev null. You can watch IOTop in the top panel to get an idea of how fast it's going. So you can see that it's being read from disk at about 350 plus megabytes per second. So let's drop the caches again, and we'll verify this with the free-m command. We can use the cgexec command to run commands in a control group. So we're going to run the dd command again, which was just reading from disk in excess of 350 megabytes a second, and apply it to our block.io test1 control group, which is throttled to 5 megabytes per second. So let's run cgexec-g block.io:test1 dd input file equals file-abc output file equals /dev/null. So this says control group execute, use the block.io:test1 group. You can get this notation from the ls cgroup command, and run our dd command using the input file-abc and output it to /dev/null. You can see up in the topmost window that IOTop is reporting that it's reading at a rate of 5 megabytes per second. Looks like it's working. What's so great about this is that we can take any application, which does not have any built-in rate limiting, and throttle it back as needed. I'm just going to cancel this as it is likely going to take a long time to complete. As you can see, 5.2 megabytes a second with throttling versus 372 megabytes a second without. In the interest of saving time, I ran several tests and plotted the output using GNU-plot. Let's have a look at the output. So we have two different files here, one represented in red and the other in blue. The y-axis is megabytes per second and the x-axis is time in seconds. The first three data points are the result of running dd without the rate limit, with the rate limit, and then without it again. We're hitting 350 plus megabytes a second in the first instance, then down to 50 megabytes a second, then back up to 350 plus. By the way, I changed the rate limit from 5 megabytes a second to 50 megabytes a second just to make the plots look nicer. Let's zoom in on the second hump here. As you can see, it flows nicely at our 50 megabytes a second limit. Then this next chunk of data is interesting. I read two files from disk at the same time, using the same control group. Let's zoom in and take a look. You can see that when the first read process starts, it quickly shot up to the 50 megabytes a second limit. But a couple seconds later, when I started the second process, indicated in blue, Then something interesting happens. Both processes read from disk at around 25 megabytes a second, for a total of our 50 megabytes a second limit. Then the red process terminates, and then the second process, indicated in blue, briefly hits the 50 megabytes a second limit and then also terminates. It's pretty cool that you can see this throttling in action. Then in this last test, I ran a process in the control group indicated in red, and then several instances without it in blue, just to compare the performance and to illustrate that you can do both at the same time. I've probably talked about this enough, so let's move on to another example using a different controller. This time let's look at the memory subsystem. In this example, we're going to look at a way to limit the amount of memory a process can use. Before we do this, let me show you the program we are going to test with. I created an example program in C called memlimit. Let's take a quick look at it and let me explain what it does. The heart of the application is a for loop that at each iteration will try and grab 1 megabyte of memory for a maximum of 50 times, and then it will print updates along the way. Okay, let's compile it and run it without any restrictions to see what it looks like. Let me just scroll up and you'll see that it says it's starting, and then it starts allocating memory, printing updates as it goes, all the way to 50 megabytes, and then it prints done. Let's go into the /cgroup/memory directory. In here, we're going to create a subdirectory called test2. Then let's change into that directory. We can list the contents, and hopefully the structure looks a little bit familiar by now. We can also run the ls cgroup command, and our new group appears in addition to the one we created earlier. Before we go any further, let's just take a look at the documentation for the memory subsystem, similar to what we looked at the block I/O controller earlier. We're going to use these two files under the memory controller. In this example, memory limit in bytes and memory mem_sw limit in bytes. These basically allow us to set the limit for physical memory and swap usage. We just need to echo our limit into these files. By the way, I found the documentation for the memory controller in the same directory as we found the block I/O document mentioned earlier. I also linked this in the episode notes below. Okay, let's configure our memory limits. Let's echo 5242880 to memory.limit in bytes. We also need to echo this value into memory.mem_sw.limit in bytes. This will restrict swap access. If we did not restrict swap access, we would quickly hit the 5 megabyte limit on physical memory, and our program would start eating up swap. So we want to make sure that we hit a hard limit. So let's test this out using the memlimit script we looked at earlier. We're going to use the cgexec command again, but this time using the memory:test2 group. So let's run cgexec-g memory:test2 memlimit. And boom, we hit the limit. The process was killed at the 5 megabyte limit. Let's take a look at the last couple lines of dmessage, where there is a couple kernel messages about our process being killed. For example, group out of memory, killed, the process number, the process name. Pretty cool. Before I wrap up this episode, I wanted to show you how to dump the running control group configuration. At the beginning of this episode, we looked at the /etc/cgconfig file, which we used to mount the /cgroup virtual file system on /cgroup. You can also use the cgsnapshot command to dump the running configuration. Let's take a look at the output. So you can see we have our mounts, then our test2 group, along with the memory limit values. Then down here we have our test group 1, along with the device rate limit. For example, you could do something like this. Redirect the output of cgsnapshot to the /etc/cgconfig file and have the settings reappear at the next reboot. And last but not least, we already covered the cgconfig service. But there is also the cgred or read service. cgred can be used to classify programs in the background and assign them to control groups. In the example that we covered today, we manually ran programs in a control group via the cgexec command. But with cgred, you can define rules and then automatically slot processes into these groups. You can do this by using the /etc/cgrules-config file to classify users, commands, or even entire user groups into predefined control groups based off rules you define. This is extremely useful since up till now we've been manually assigning tasks into control groups. We barely scratched the surface of what control groups can be used for. You can do similar things as the examples we just talked about for CPU and network resources. Never mind all the monitoring and accounting information that you can collect. So if you need to manage resources on a machine, be it for process segregation, managing virtual machines, or Linux containers, you should really check out control groups. Alright, that concludes this episode. Thanks for watching. If you would like to get notified about future episodes, please subscribe to my mailing list. You can do this by going to the Get Notified link in the header and entering your email address. Have questions, comments, or concerns about this episode? What about episode ideas? I'd love to hear your feedback, either good or bad. Shoot me an email, justin@sysadmincasts.com.